Now, as it has only recently launched, the portal is not yet populated, but we are currently working on improving its content. So before we jump into the presentation, let's do quickly some of the housekeeping. Let's review a few notes on the functionality of the On24 platform, which we are currently all using. In this platform, all windows are resizable and movable, so feel free to move them around or close them to get the most out of your screen space. The slide area and media player window can be maximized to full screen by clicking on the arrows in the top right corner of each window. And if by chance or by mistake you minimize or close a window, don't worry, you can click on the corresponding icon on the toolbar at the bottom of your screen to reopen it. So we have the media player and we have the slides. Those are the two most important items during our presentation. So if you miss anything on those two, just click the icon at the toolbar. Please note that the audio for this webcast is being streamed through a computer, and because, as you can imagine, webinars are bandwidth intensive, we recommend closing any other programs or browsers you have to reduce the potential for connectivity issues. If you find you're having technical issues with your audio or your slides are delayed for some reason, please try pushing F5 on your keyboard to refresh the page. A closed captioning system is also offered, but unfortunately only for the on-demand session. So for those watching this session on demand, you can turn on the live closed captioning by selecting the CC icon in the media player. Now, this option works very well with regular English, but if we start using engineering terms, it sometimes doesn't recognize them correctly. But still feel free to activate it if that would help you follow our presentation better. All resources, Q&A, and presenter contact information are available in the on-demand session as well. And additional material is also available, as we said, in the related content field. And we encourage you to download any resources and bookmark any links that you may find useful. If you have questions during the presentation, you can always submit them in the Ask a Question window. I'm alone today, so I will try to address all those questions, most probably at the end of the presentation. And a reminder that this session is being recorded and it will be available on demand within 3 to 4 hours after this presentation. And it will be accessible using the same link that you used to join this webinar. The Coffee Corner is a Bentley-wide program. Bentley offers different Coffee Corner webinars with technical content for various products and, of course, for geotechnical analysis focusing on Plaxis. It also has an Open Ground, MicroStation, ProjectWise, Synchro, civil applications, Open Roads, Open Bridge, Open Rail, Open Flows, and Open Buildings. And our structural packages are also there, so go to bentley.com/events to sign up for any related application that you are interested in. Also, I just want to make sure that everyone is aware that we do have some digital currency newsletter out there for various products. It's a collection of helpful industry-focused digital newsletters delivered right to your inbox. So if you are interested in subscribing to any of those newsletters, simply scan this QR code that you see on the screen, and you can get access to subscribe to those newsletters. I will leave that up for a few seconds. Maybe you want to scan it. All right. And most importantly, know that your opinion matters. You can fill out a survey, as I said, by clicking on the icon at the right side of your toolbar, or maybe you can wait for it to pop up automatically when the session ends. We always review your feedback, not only to improve ourselves and make sure that we give you an optimal experience, but also to learn from you and to understand what you want to see in the upcoming sessions. So if you have any ideas, wishes, don't hesitate. Just write a comment on that survey and we will take that into account for our next learning sessions. And finally, after watching this session, live or on demand, you will receive a Bentley certificate for attending. It will be added to your transcript, which you can find at learn.bentley.com/transcript. Note that this transcript will be tied to the email address that you used to sign up for today. So if your Bentley account has the same email address as the one that you used to sign up, then those two will be matched and the transcript will be added automatically to your account. All right, so those were the housekeeping rules. As mentioned at the beginning, today's focus will be on construction dewatering, which is, of course, an essential topic in geotechnical engineering. and we'll explore some of the fundamental concepts, starting with a brief introduction. And from there, we'll delve into the definition and generation of pore pressures, as well as the various pore pressure calculation methods that are available in Plaxis. Next, we'll examine practical dewatering scenarios. And finally, I'll wrap up with some key considerations. So let's get started. So let's discuss dewatering today. And dewatering has always been a fundamental aspect of construction, as you can imagine, and also of mining projects in the presence of groundwater throughout history. Now, in the older days, dewatering began with very simple gravity-based methods, and it evolved with mechanical devices over time. And by the 1940s, the approach to dewatering became much more scientific with the integration of geotechnics and hydrogeology. Of course, there are many investigations according to which most problems encountered in deep excavation have direct or indirect relations with groundwater. Therefore, whether groundwater has been properly dealt with is obviously a crucial point for the success of construction and excavation, more specific. Now, one of the many reasons why groundwater-induced problems in an excavation may arise is, of course, from an insufficient investigation of groundwater or of the geological conditions that lead to the inability to fully control the groundwater. But it may also arise from a misunderstanding of the influence of the groundwater, so that a wrong excavation method is in the end adopted. And here you can see two prime examples of groundwater-induced problems. I always like to start my presentation with some scary pictures, and keeps everyone on their toes. So on the left, we have a failure of a shoring system that has no dewatering in place, and this failure came about due to a heavy rainfall. And on the right, we have a collapsed cofferdam due to the failure of the dewatering system, causing a higher hydrostatic pressure than the designed ones. So one of the goals of dewatering is, of course, to, as you can imagine, to keep the excavation bottom dry. Now, with the higher flow velocity of groundwater, especially in sand or gravel, groundwater may well flow into the excavation zone, which, of course, will cause inconvenience for the construction people. So to keep the excavation bottom dry, the groundwater level is generally lowered half a meter to 1 meter below the excavation surface, as you can see in the figure at the bottom left. Now, usually when we have, of course, an excavation in less permeable soils like clay, there is no need to lower the groundwater level to that elevation, as the groundwater flow is so slow in clay soils that flowing of groundwater into the excavation zone will mostly likely not occur. Secondly, dewatering is established to prevent leakage of groundwater or soils. To excavate in sandy or gravelly soils with a high groundwater level using either soldier piles or seat piles, which may not be perfectly watertight, or even diaphragm walls or board piles where you have joints that may have some kind of defects, will of course risk the possibility of the leaking of groundwater into the excavation zone through the retaining wall. And this is something that we are going to examine a bit at the end of the presentation. Now, the leakage of groundwater and soils may, of course, lead to disastrous results and bring about collapses and failures of excavations in the worst case scenarios. When the leaking is so big, it's so great that it is enough to enlarge the holes in the retaining wall. Thirdly, we have dewatering, and we use that to avoid sand boiling. As we said, keeping the excavation bottom dry when excavating in sandy or gravelly soils requires lowering the groundwater level within the excavation zone to half or 1 meter below the excavating bottom at least. And while the excavation proceeds, the difference between the groundwater levels within and outside the excavation zone grows larger, as you can see in the figure at the bottom right. And when the hydraulic gradient around the excavation bottom grows larger or equal to the critical hydraulic gradient of soils, then sand boiling will occur. Of course, many methods are available to avoid sand boiling. One of them is, of course, to lower the groundwater level outside the excavation zone. However, the possibility of ground settlement outside the excavation zone has also to be considered. The fourth is to forestall the upheaval failure. Now, as shown in the figure at the top right, there exists a permeable layer, such as a sand or a gravel, underlying the clay layer. So what happens is that the water pressure from the permeable layer will generate an upheaving force against the clay layer. And when the water pressure acting on the bottom of the clay layer is larger than the total weight of that layer, then upheaval failure will occur. And one of the methods to prevent the occurrence of upheaval failure is to lower the piezometric pressure of the permeable layer by, of course, pumping. And finally, we use dewatering to keep the basement from floating. Now, as it is natural, with the completion of the excavation, we start constructing the basement of our structure. Now, in sandy soils, with the light weight of structures during the stage of basement construction, where the weight of the basement is only considered, the phenomenon of floating of the basement is likely to happen if the weight of the structure is smaller than the water pressure acting on the foundation base. Now, once the floating phenomenon has happened, then you have differential heaves, you have a floating basement, which most likely will not necessarily sink back to the original elevation. And then you have the construction moving forward, which of course may lead to damage to the structures. And in the worst case scenario, the basement may need to be demolished or reconstructed. Therefore, dewatering is usually required at this stage of basement construction to keep the upheaving force on the foundation bottom smaller than the weight of the structures during construction. So, having talked about what is construction dewatering and why we need it, let's now move forward to some of the basic concepts of pore pressures. And let's start with the part where we define what pore pressures are. As we know, in general, the water in the voids of an element of saturated soil will be under pressure either due to the physical location of the soil or as a result of some kind of external forces. This pressure is the pore water pressure, which we note here at the bottom right as PW. And the question is, how do we calculate these pore pressures? So we either calculate them separately based on the phreatic level and the undrained behavior that our, of course, soil exhibits, and this is the excess pore pressure analysis, or we calculate only the total pressure, which is the total pressure analysis, or as we call it, a total head analysis. Now, in a finite element analysis, it is useful to divide pore pressures into different terms because there are different options for the way each of those is calculated. For example, the pore pressure due to the phreatic level is called P steady, whereas the pore pressure due to the undrained behavior of our soils is called P excess. And finally, we have the total pore water pressure, which we call P water, and it is the sum of the steady state and the excess pore pressure, as we will also see in the next slide. And here we have a more visual representation of the three types of pore water pressures. This chart is taken from Andrew Lee's book on geotechnical finite element analysis. It is, in my opinion, an excellent introduction to the topic. And the chart shows you the relationship between the steady state pore water pressure and the excess pore water pressures that are calculated by the kernel. So the steady state pore pressure is, as we said, the pore pressure arising from constant hydraulic boundary conditions. For example, that could be a stationary groundwater level. And this part of the pore pressure does not change with time during a displacement or a consolidation analysis. However, it is possible to change the hydraulic boundary conditions in the analysis states to establish a new steady state pore pressure distribution. On the other hand, we have the excess pore pressure, which is calculated by the kernel, and is the change in pore pressure from the steady state value caused by either the loading, unloading, or maybe due to a rapid change in the hydraulic boundary conditions in undrained or consolidation conditions. And excess pore pressures will, as you can see here, dissipate to zero during a consolidation until steady state conditions are restored. And on the third column on the right is the total pore pressure, which is the actual value of pore pressure at a point at a particular time, and it will be the sum of the steady state in the excess pore pressure. So starting from the top to the bottom, we have different simulation stages. We start with the in situ conditions where we establish our steady state pore water pressures in the initial phase. And naturally, we have zero excess pore pressures. And then we move to the installation of the retaining wall and our dewatering, which changes, as you can see, the pattern of our steady state pore water pressures. And it also generates positive excess pore water pressures. Then we have a consolidation step where these excess pore pressures are dissipated. And finally, we have our excavation and loading step and one final consolidation step. So this is an example of how the steady state and excess pore pressures are changing throughout the stage construction. So as we saw in an excess pore pressure analysis, we have the steady state and we have the excess pore pressures. So the question now is, how do we determine those two types in Plaxis? And the steady state pore water pressures can be generated by either assuming a hydrostatic condition using a phreatic line input, which is either with a global or a cluster approach, or they can be generated through the use of a steady state groundwater flow. Now, as we have mentioned in the previous slide, it is important to note that the pore water pressures do not change with time during a displacement or consolidation analysis. However, it is possible to define or redefine the hydraulic boundary conditions in an analysis stage in order to establish a new steady state pore pressure distribution at different phases. And on the other hand, we have the excess pore water pressures, which are generated, as we said, due to the change in pore pressure from the steady state value caused by loading, unloading, or a rapid change in the hydraulic boundary conditions. And these pore pressures are, again, dependent on the constitutive model. So they are relevant for a plastic analysis where it becomes dependent on the drainage behavior of the soil. By drainage behavior, I mean the undrained A, undrained B, or undrained C. And for a consolidation analysis, where it is controlled by the permeability of the soil. So for plastic, we have the undrained behavior, and for consolidation analysis, we have the permeability of the soil that actually control these the excess pore pressures. Now, although we are not going to talk about the total pore pressure analysis any further in this presentation, it is worth mentioning a few things about it and also when we want to use it. So this type of analysis can be used only in a fully coupled flow deformation analysis. And just to refresh everybody's memory, a fully coupled flow deformation analysis is used when it is necessary to analyze the simultaneous development of both the deformations and the pore pressures in any saturated or partially saturated soil as a result of a time-dependent change in the hydraulic boundary conditions. So we expect our flow field to change in time, and therefore we have a transient flow, essentially. Now, a case where this analysis is used is, for example, when we want to include the drawdown of the reservoir level behind the dam, or maybe we have an embankment dam which is subjected to tidal waves. So it is close to the sea, and we have tidal waves that change with time. So that means that the outer water level will change in time, and it also has an effect on the pore water pressures inside our soil body. And for that, we need to use, of course, a transient groundwater flow analysis because our boundary conditions will change over time. Now, is a fully coupled flow deformation analysis relevant to construction dewatering? It is, especially in cases where you have, let's say, a relatively fast building process in a partially drained excavation, and you maybe use wells to pump out the water and keep the excavation dry. And of course, these situations can also be simulated using transient groundwater flow to make sure that we take this whole transition properly into account. Now, let's move on to how we can define those pore pressure calculation types in Plaxis. As you may be aware, Plaxis offers two options for dealing with changes in pore water pressure distribution, and I will go into more detail later. As you can see on the right, these options are available in the phase calculation window under the pore pressure calculation type option. Now, the first one, which is also the default one, is called the phreatic method. And it's called phreatic because it is based on phreatic levels. So what it does, it will calculate the pore water pressures according to the hydrostatic distribution based on the phreatic levels that we have defined in Plaxis. And next to that, Plaxis also offers the possibility to compute pore water pressure distribution using steady state analysis. And here, Plaxis will perform a flow calculation to determine the steady state pore pressures and the phreatic level based on the hydraulic conditions. A third option is also offered, and it's called use pressures from previous phase. So what this option does is that it copies all the pressures and flow velocities, wherever that's applicable, from the parent phase as an input for the current deformation analysis. Of course, as we saw in the previous slide, a transient analysis is also possible, but you need to be working in that case in a framework of a fully coupled analysis, which, as we said, we are not going to cover in this introduction. Now, starting with the phreatic method, which is also the default calculation type, we said that it calculates the steady state water pressures based on the input of a global water level and the water conditions of the clusters. The global water level is by default based on the positions of the water level that we have defined in the borehole definition window. And you can also change that in the flow conditions mode, here in green, where you can create additional phreatic lines. So in the flow conditions mode, we can also change the water conditions of each individual cluster, if that is necessary, of course. And here we have 4 different options available. Now, as we said earlier, a cluster can be assigned to a global water level, which means that in active soil clusters, Plaxis will calculate the steady state pore water pressure based on the location of the global water levels. And based on that, it will also calculate the external water pressure or the water loads on the external model boundaries. But we can also create additional water levels, as many as we want, it doesn't matter, which we call the custom water levels. And as we will see in a second, there are some difference between a global and a custom water level. Now, in addition to that, it is possible to remove water pressures from individual groups or clusters in order to make them dry. An important thing to note here is that the activation of water can be done independently from the soil itself. So let's say that we have deactivated a soil cluster and the water level is above the excavation level. So then there is still water in that excavated area. Now, if we intend to simulate a dry excavation, then the water must be explicitly deactivated. In that case, we can set the cluster to dry. So the dry clusters will behave as non-porous materials. This means that as a result, neither the initial nor the excess pore pressures will be taken into account, and also flow is not possible throughout that cluster. And finally, it is possible to generate pore pressures in soil volumes based on the pore pressures of the adjacent soil volume, so the soil volumes above and below that cluster. by selecting the cluster and then selecting the interpolate option. So this option is, for example, used if we have, let's say, a relatively impermeable layer, which is located between two permeable layers. So it's like a sandwich of permeable, impermeable, and permeable again. So the pore pressure distribution in the impermeable layer will not be hydrostatic, as you can imagine, so it cannot be defined by means of a phreatic level. So it's best to use the interpolate option in that case. So let's see an example. Now, we have those two cases. In both left and right cases, we have three identical layers, each with a different water condition. On the left side, layer 1 is assigned to a global water level, which is located approximately at the middle of the layer. And layer 3 is assigned to a custom water level located above the ground. And of course, for layer 2, we chose to interpolate the pore pressures. And on the right side, the custom and the global water levels are reversed. So layer 1 has a custom water level at the same elevation, and layer 3 is the one that has a global water level. So what is the difference between the left and the right cases? As you can see, the distribution of pore water pressures within the soil is identical. In layer 1, we have the pressures that start from the middle of the layer and then increase hydrostatically linearly until layer 2. And at the top of layer 3, the pressures start from a value that corresponds to the phreatic level above our ground. And for layer 2, we have a linear vertical interpolation starting from the value at the bottom of the soil volume above and ending at the value at the top of the soil volume below. Now, the only difference is that in the right case, we also have an external water load. And this is because the global phreatic level is located above our soil in an inactive soil cluster. Or to put it in more accurate terms, it is outside our active geometry. So this is something to be aware of, and this is something that I also mentioned in the list of the global water level. And here is an example of pore water pressure distribution using the phreatic method. What you will observe is that there is no, first of all, that there is no flow taking place. You will just have hydrostatic distribution of the distribution, and of course, as you can see, the phreatic level and the piezometric line will remain parallel to the defined reference water level. So by using this method, you need to really have a clear idea of what the water level will actually look like and how the water distribution will be in your model. Now, let's say that you don't have a clear idea, and that's understandable, then we do recommend that you use a groundwater flow. So then you first have to switch the pore pressure calculation type to a steady state groundwater flow, and then provide some additional parameters to the model. So now the updated pore water pressure distribution will be obtained based on an additional finite element calculation that will be performed by Plaxis for the water only, based on the mass balance equation of the water. And for that, you need to define two additional sets of parameters. First, like any finite element problem, you need to define the boundary conditions for the flow problem. So you need to go around the model and tell Plaxis whether the boundary conditions are going to be closed, or maybe allow seepage, or maybe they are at a fixed head. And the second one will be to define the material properties of the soil in terms of permeability. So for each material, you need to provide permeabilities in both directions, that is Plaxis 2D, or 3 directions in Plaxis 3D. And you will, and of course, if you are also considering an unsaturated zone, you may also need to provide additional retention curves that would describe the behavior of the unsaturated zone in terms of pressure versus degree of saturation and pressure versus relative permeability. Another difference is in this type of calculation is that the default boundary condition is a head condition based on the position of the global water level, and that the phreatic level is not an input, but it is the result of the calculation for an infinite amount of time. So what's important here is the intersection points of the water level with the active model boundaries, and the program will calculate flow boundary conditions in terms of groundwater head corresponding to the water level. So let's say the internal part of the water level is not used, and it will be replaced by a phreatic level resulting from the groundwater flow calculation. As such, the water level tool, in this case, is just a convenient tool to create boundary conditions for a flow calculation. And here is an example of a pore water pressure distribution using a steady-state groundwater flow method. You can see a few things. You can see that we now have water flowing inside the excavation. And you will also see that the piezometric line starts following, let's say, a more complex shape. Considering the situation, considering the boundary conditions, and of course, as we said, the different permeabilities that we introduced to the model. So this is how we could potentially perform dewatering in Plaxis. And to sum up those two methods, in short, the phreatic pore pressure calculation type generates directly the steady-state pore pressures from the phreatic level and from the cluster-related conditions. And it also has the position of the phreatic level determines the distribution of the pore pressures based on the hydrostatic distribution, and the head is kept as fixed, so it is constant. And on the other hand, the steady-state groundwater flow pore pressure calculation type determines the steady-state pore pressures and the phreatic level based on the hydraulic conditions that we give to as an input. Also, the position of the phreatic level influences the water conditions only at the model boundaries, and the distribution of pore pressure is calculated from a flow analysis based on the boundary conditions and the permeabilities used. And the flow analysis is prescribed as time-dependent flow equilibrium with time equal infinite. So it is, let's say, a long-term analysis. So let's move forward to modeling dewatering. So if we're talking about dewatering of an excavation, which is the topic that we're discussing today, we can start with the example of submerged excavation. Now, in this example, we will excavate our deep excavation without changing any of the water conditions. So we can do, let's say, the stage construction all in one go. So this is what happens. We excavate our first step, and as you can see, we still have water inside the excavation because we haven't changed anything in the water conditions of our model. Now, as you can see, the phreatic level is higher than the excavation level, and therefore the water stays there. So this is a case where, for example, we have a very high water table, and we may want to take advantage of the water pressures inside the excavation as a resisting mechanisms to the deformations of the retaining wall. And we keep excavating, and at the bottom we apply a stabilizing weight to avoid having an uplift problem, but also to so we can have, let's say, a watertight connection with the retaining wall. And when that happens, we can then remove the water from the excavation. Then we have, of course, a dry excavation. And we can do that by using the cluster dry option, or you can do that, of course, using the cluster phreatic line, which of course, you put the phreatic line below the excavation. Of course, in both cases, it assumes that we use the phreatic method. Now, what happens here is that the pore water pressure outside the excavation area remains unchanged. This might be, let's say, a very realistic restriction on your building process, that you do not change any of the external phreatic level. Because maybe you have some kind of buildings, you have adjacent buildings that are present, and then maybe they have an old foundation system with wooden piles, as is the case here in the Netherlands. So if we lower the water table, they might become, those piles might become dry. That would cause all kinds of processes that will deteriorate the foundation. So let's say this is quite straightforward method. We can also have an undrained excavation. For instance, you are doing an excavation in pure clay, which happens relatively fast. So for every excavation phase, what we do here is that we excavate the soil, and then we set the excavated area or volume in Plaxis 3D to cluster dry. Now, this method only works if we only want to consider the undrained excavation. So we let's say only when we want to assess the short-term conditions. And we repeat the excavation steps, and then, of course, with each excavation step, we set the clusters to dry until we reach the bottom of our excavation, and then we apply a stabilizing weight at the bottom. And again, here the phreatic level outside the excavation remains unchanged, and that's because we assume that the permeability of the soil is so low that it will not react to our excavation. So we would say that this is only suitable for short-term excavations in soils with very low permeability. On the other hand, we can do a drain excavation, and for a drain excavation, what we do is that we excavate the soil, and again, this is an ideal case where we are also going to do a long-term excavation, and we also have highly permeable soils. So we excavate the soil here, and then we define the boundary conditions. So basically, we define our we apply some kind of external boundary conditions here at the let's say at the left and the right boundaries, where we apply a head which is equal to the elevation of the groundwater level, and then of course we also do that in the excavation level, where we apply a groundwater head which is equal to the elevation of the excavation bottom. And this assumes that we just put pumps at the bottom of the excavation, and then we are removing the water there. So we are not doing any kind of deep wells or anything else. We just pumping water from the surface of the excavation. So we have excavated our soil, and we have defined our boundary conditions, and then we perform a groundwater flow analysis, and you will see that the analysis will give you flow around the retaining structure, and also a bit of lowering of the water table just below the retaining wall. So this is, let's say, our steady state solution. It is the solution at the end of time. And then we repeat the excavation, and we can see that the water table becomes a bit lower, and we continue until we reach the bottom of the excavation, and then we apply the stabilizing weight. And after that, we stop with dewatering, and the situation can return as it was before, and the groundwater head outside the excavation is again at its original position. So this situation is, let's say, suitable for long-term excavation in soils with high permeability. So I've used a lot the terms drained and undrained, right? But what do those terms actually mean? Undrained means that no water flow, so the volume of voids in saturated soils remains unchanged, and the soil density also remains constant. Now, since water is essentially incompressible in comparison, of course, with the soil skeleton, any imposed loading is transferred directly to the pore water, and it is transferred as, of course, excess pore pressures. And the effective stress remains constant, while any attempt to impose volume change is resisted by the excess pore pressure changes. Now, these changes are we have that in undrained, let's say, case where the rate of loading is high relative to the soil's permeability, which occurs in most constructions in stiff clays or during particularly high rates of loading, such as, for example, an earthquake acceleration. On the other hand, drain means that the water is free to flow through the voids of soil, such that the void volume changes will occur, and such that no excess pore pressures will develop. Now, any loadings result in this case, in total stress changes that equal the effective stress changes, since we don't have any excess pore pressures. And these conditions occur when the rate of loading is relatively low compared to the soil's permeability, which occurs in most construction activities in sands and gravels. So when are drained or undrained assumptions then appropriate? Now, as we said, if the rate of loading is sufficiently high relative to the soil permeability, such that no significant dissipation of excess pore pressures occurs during the loading itself, then an undrained analysis is appropriate. As we said, for most practical cases, this includes construction activities in stiff clays. However, and this is something that I need to underline here, it is wrong to assume that all clay soils behave in undrained manner. So, for example, normally or lightly over-consolidated clays may behave in an almost drained manner because they have quite thin deposits and maybe they also have sandy or silty laminations that actually shorten the drainage path lengths. So Vermeer and Meyer in 1998, they proposed an undrained assumption that may be appropriate when the degree of consolidation is less than 10%, or the time factor, which is the uppercase T, which is also a unitless, and it's calculated by this equation here, is less than 0.10. On the other hand, if, let's say, the rate of loading is sufficiently slow relative to the soil permeability, such that no significant excess pore pressures are generated, then a drained analysis is appropriate. And for most practical cases, as we said, this includes cases where we have construction activities in granular soils, such as sands or gravels. So again, Vermeer and Meyer also propose that we can consider drained assumptions when we have a degree of consolidation higher than 70% or a time factor higher than 0.4. So the next logical question is, what happens in between? Now, in cases where the rate of loading falls between the limits of drained and undrained behavior, let's say that we have excess pore pressures that develop and then they partially dissipate during construction, then maybe it is necessary to also include a consolidation analysis. And this tends to occur when simulating construction activities in, as we said, normally or lightly over-consolidated clays, or maybe silts, or maybe any mixed soils with a significant clay content. So where do all this fit in? Now, we have some solutions here. If you look at the solutions, for the left solution, time t is 0, which would mean that it corresponds to a short-term situation. Basically, that is the undrained condition that we have defined. And then we have the other extreme. Let's look at the right solution, for which time t is infinite. Basically, it is the long-term solution, or rather the very long-term solution at t equal to infinite. These are the two extremes, and of course, what happens in between is once we do a quick excavation, then near the excavation bottom, we see that the pore pressures will go to 0 at the excavation bottom, and they will have a transition to the hydrostatic pore pressure, which was there before we did the excavation, which is here. And if we wait a bit longer, then of course, we have this transition here, and if we wait a bit longer to go to t equal to t2, then of course the influence zone will become larger because the water has time to react and to flow out of the soil body. And finally, after we reached an equilibrium situation, in which we see that the water table on the active side of the excavation has lowered a bit, as you can see here, then on the passive side, we do have a nice pore water pressure distribution, which is shown also here. So how can we solve this using Plaxis? Now, what we can do is that we have the short-term solution. So we can just use the water levels with the phreatic method. So we are going to excavate our soil, and then we have to rely on the undrained soil behavior for the strength. And if we go to the long-term solution, the right hand, we can use the water level with the phreatic method in combination with the interpolate option, which we'll also see in a few seconds, to make this a nice transition from the dry excavation to the soil pore pressure distribution below the excavation. Or you can just use a steady state groundwater flow using the boundary conditions that we have mentioned in the previous slides. And if you look at the two situations in between, basically it's a transient condition that we want to model. So we can define that kind of situation using water levels, and we can use a transient groundwater flow using a specific time interval. So t equal to t1 or maybe t equal to t2. And then we just let the calculation give us the resulting pore pressure distribution with time. We can also use the interpolate option. So basically, we can select the zone where we want to have this kind of influence. But that means we have to also do a simplification. So for instance, in this case, we do this kind of simplification here with the red lines. See, so the first part we say that we'll make a small zone, maybe 1 meter or 2 meters, depending on what kind of soil you have and how long your excavation will be open. And then you just define a zone in which you can use the interpolate option on that cluster. And if we wait a bit longer, the zone of interpolation becomes deeper, and we can also have different distributions here. So with the interpolate, we do, let's say, a simplification where we are going to assume a linear vertical interpolation of the pore pressure values. So let me pause here for a few seconds. We have seen the different methods of dewatering and how you can do it in Plaxis. So my question is, if you are performing dewatering in your projects, let's say, how do you typically do that? We have some options here. We have the phreatic method, as we said, the steady state groundwater flow method, transient flow method, or fully coupled, or maybe you don't necessarily encounter dewatering, and then you can select option D. So again, how do you typically perform dewatering in your construction projects using Plaxis, phreatic method, steady state, transient groundwater flow method, or you don't have dewatering? And we can discuss it at the end of the presentation. I will leave that for a few more seconds. Okay, thank you for looking in your answers. Let's move on to the last part of the presentation, which are the general considerations, maybe general, but also very important. So having talked about construction dewatering, something that we see a lot in technical support is what we call the Z-shaped water level. So as you can assume, we want to draw the water level at a higher elevation outside the excavation and then drop to the lower elevation inside the excavation site. So what many users do is that they draw a horizontal line at a higher elevation and then drop vertically at the retaining wall and then continue with another horizontal line at the bottom or below the excavation. And of course, this is an incorrect use of the phreatic levels, and you should definitely avoid it. We did another webinar, which you can find in the related content. It is called Excavation Dewatering and Common Pitfalls. And essentially, it analyzes in detail the right and wrong ways to model the water conditions inside the excavation. So if you haven't already, I recommend that you watch it to get some useful information on why some methods work better than others. So why this method doesn't work? Well, if you look closely at the pore pressure distribution that you see at the front, you will see that on the active side, we have a nice pore water pressure distribution. And also on the passive side, below the excavation, also a very nice distribution. But what we also see here is, if you check below the retaining wall here, is that we have sudden jump in pore pressures between the left and the right pore pressure distribution, which is seen here in the zigzag area. And obviously, this is incorrect, and this can, of course, create also a few problems, because a wrong pore pressure distribution acting on the wall will likely also give you incorrect deformations and forces on your retaining wall. So then, what other options do I have? One option is to set the excavated soil cluster to dry, as seen on the left, with a gray color, or use the head option with a value equal to the elevation of dewatering, as seen on the right, with the green color. Again, I use both cases with the phreatic method, so there is no groundwater flow. Now, why these methods might not work as expected? In the left case, we have an initial pore pressure distribution, and then we set the cluster to dry. So this will now make the distribution look like this. So we have an initial pore pressure distribution. We see that here the pore pressure distribution just below the excavation bottom is not zero. And since there is no resistance at the top of the excavation, so we have no excavation and we have no load, then we might get into some kind of heaving problems. And since there is no, in this case at least, there is no tensile strength, the soil will fail locally in tension. So we get some heave, and as you can see here, we have some white plastic points near the excavation surface at the bottom. These are tension cutoff points, which give us an indication of a tensile failure. And in the right case, we have the same initial pore pressure distribution, and then we set the water conditions of the cluster below the excavation to head, which is here shown in green, and then we assign a head value. So essentially, we are creating a transition here, as you can see, and a jump in the pore pressures. And again, this creates an out of balance in our pore pressures, which creates a significant heave at the bottom of the green layer, which is almost like an outburst of the layer. And as we can see in the plastic points underneath the layer, which we have defined with the head condition, there are a lot of red and white plastic and tension cutoff. So those two methods will potentially give us the wrong pore pressure distribution. And again, I encourage everyone to check the webinar that we did that explains everything in more detail. So then, what is the recommended method? And so when we want to perform dewatering using the phreatic method, this is the recommended method that we show here. Essentially, what you want to do here is to set the excavated cluster to dry, as we saw in the previous slide, because of course we don't have any water inside our excavation. But we also want to have a nice transition. So this is the initial distribution, and then we set the top cluster to dry, and then we said, let's get the two clusters underneath the excavation and set the clusters to interpolate pore pressures. So what will Plaxis do? It will turn the cluster to an orange color, which will give you a visual indication of the conditions applied, and then we have a proper definition of pore pressure. So in case you're using dewatering with a phreatic method, then you definitely want to use the interpolate pore pressures underneath your excavation. And this will give you the correct distribution, as you can see here. Now, a few slides back, we talked about pumping water at the surface of the excavation, but if you want to have deep wells installed below your excavation, such that the phreatic level in this part will be below the excavation bottom, you can use one of these two options. We have the well elements, and we have the drain elements. So if you use a well, you can directly specify a discharge, a value for the extraction, and the new phreatic level will be the result of this extraction. On the other hand, you can use also a drain element, and with a drain element, you can specify that wherever the drain is located, the pore pressures are equal to zero. And then the drain will calculate what kind of discharge it will need to reach that. So you can use a well element when you want to specify the discharge, or you can use a drain element when you want to make sure that you get a specific pressure definition there. In the example that you see here on the right, we see an excavation with two vertical lines representing the wells, for which we have defined an extraction rate. So if we run a groundwater flow calculation, Plaxis will calculate what the lowering of the water table will be based on the extraction that we have given. And finally, if you have a retaining wall which is of a permeable type, such as, for example, soldier piles, where there is a gap between the piles, where water, of course, can seep through, then we need to consider a couple of things, especially when we want to choose to model that pile wall as a plate element. And we usually model those plate elements in combination with an interface, which gives us the possibility to define a cross and a parallel permeability for that wall. Therefore, using an interface will allow us to simulate the seepage through the pile walls. Of course, again, this becomes relevant only in situations where we have a groundwater flow. So it has to be either a steady state groundwater flow or a fully coupled flow deformation analysis. And as you can see here, by selecting the interface in the selection explorer, a checkbox, as you can see here, is available to make the interface either active in flow or inactive in flow. This has, of course, consequences for the actual interface permeability that is being used in a selected calculation phase. So by default, when an interface is active in flow, which is also the default option, we have zero cross permeability, which means that the interface is impermeable. On the contrary, if the interface is inactive in flow, then the interface is fully permeable. Of course, this will depend on how we define the interfaces in the material definition. Here we have also the option to make our interface semi-permeable, which allows us to define a specific value for the hydraulic resistance of the wall. Now, I can understand that it's not always easy to determine the hydraulic conductivity of a wall, which is, if I'm not mistaken, usually measured as the total discharge through the gap for a given head difference and for a given length of the gap. But I guess this might be also a topic for a different coffee corner. So to summarize my presentation, because I think I went a bit overboard, today we have covered the introduction to the topic of construction dewatering. We have seen how the different pore pressures are defined and generated in Plaxis. The available pore pressure calculation types that also are available in Plaxis. And we have made a distinction between undrained and drain excavations. And finally, we have discussed some general considerations, more specifically some ways to model dewatering using the phreatic calculation. Some were correct and some were incorrect, as well as some dewatering components like wells and drains and how to deal with permeability in walls. I hope you found this presentation useful and informative. I invite you to submit any ideas you have in the survey form that you will receive at the end of the presentation, or directly in our ideals portal, which you can find in the resource list in the links below. I think we have a few minutes more to answer some of your questions. So just give me a second to go through the questions. Okay. Eric asks, how do you evaluate the water discharge at the bottom of the excavation? This is a very nice question. Actually, I was thinking of including that in the presentation, but unfortunately, it became my presentation became too big, too fast. So maybe it's something to also analyze in the next coffee corner. So one way to evaluate how much water you need to, let's say, take out of the soil to be able to reach specific boundary conditions that you have defined is, of course, to plot the flow. So you go to the stresses menu, and then you select the groundwater flow, which will give you the maximum and minimum flow values in your model. And then what you need to do is to create a horizontal cross-section at the bottom of the excavation, or just a bit below the excavation, from one side of the retaining wall to the other. And that will give you the water discharge at the bottom of your excavation. Boris asks, would you use the fully coupled flow analysis for excavation of soaring walls or shafts? Personally, I would. I love fully coupled flow deformation because you have the ability to model, like we said, the simultaneous deformation and changes in deformation and pore pressure. It takes a bit more time, depending on, of course, the complexity of your model. But I mean, personally, I would, but maybe it's better if you started with a simpler phreatic or steady state, and then later on in your design, maybe you want to also perform a fully coupled to see how much difference you get, because it's usually a calculation type that takes more time to complete. Another thing that you need to account for is that the fully coupled flow deformation also always assumes that you have suction or you have an unsaturated zone. So it's not something that you can switch off in your analysis. Whereas in a plastic calculation, you can always do that. So another question from, sorry, it's so many. Andrei asks, can I use the steady state groundwater flow if I don't have any values for the permeabilities of my soils? That's also a good question. So ideally, you will need to have some kind of permeability values for your soil to accurately model your groundwater flow. It's an input for any steady state analysis or for any like consolidation or plastic steady state analysis. So you will need to give Plaxis some kind of permeabilities. Now, if you don't have those values, it's also understandable because they're not readily available always. So if you don't have specific data, then you can always use, let's say, general estimates based on the soil types. And of course, sandy soils tend to have higher permeability than clay soils. Plaxis gives you the option to use some default values for the permeabilities based on the type of soil that you have. So if you go to the material definition, then you go to the groundwater tab, then you have the option to use the default values, which in my experience are not accurate, but at least pretty good. So you can use that if you don't have anything. But you need to also remember that you need to define in a steady state analysis also the boundary, the flow boundary conditions. So you need to, like we said, go around your model, and then tell Plaxis what is closed, what is a flow, what is a seepage. So you need to be a bit more meticulous in how you define your boundary conditions. I see quite a lot of questions. I will try to respond to one more, and I apologize for not responding live, but I will follow up with you during the week. So Saleta asks, could you have only custom phreatic levels instead of a combination of global and custom? And would, in this case, the custom levels would be equivalent to the global level? Yes, you can. Like I said, the only difference is that you need to be aware of is the cases where you have, the only difference between a global and a custom water level is that you have this situation here. So in case you have a global phreatic level outside your active model geometry, as we saw here in the right case, then this will result in an external water load, which is normal. If you do the same thing with a custom water level, you don't have this external water load. So typically, the results will be equivalent, but you only need to be aware of this situation here. I can get another one. Mark Edward asks, on steady state seepage, it is necessary to input soil permeabilities, or they will have the same result no matter what you... no, they will not have the same result no matter the permeability. It is necessary. It is so if you run a steady state analysis and you don't have permeabilities for your soil, first of all, the calculation will not start. It will give you an error message saying that, hey, go back and give me something. And those permeabilities will definitely have difference in the results, because essentially what Plaxis does is that it runs finite element flow calculation. It will be based on the the water mass equilibrium. So, and in those, of course, in the Darcy equation, the permeability is also included. So they will definitely have a difference. All right. One last. Pavel asks, short-term excavation with low permeability. Can you give an example for short-term? A couple of weeks or a couple of months. And could you also give an example of low permeability? It's difficult to tell you exactly a range of numbers that are low permeability or high permeability or long-term, short-term. And that's why I gave you, let's say, this slide where we have an approximation of what an undrained and drained situation is. So if you see here, we have different values like T, which is the construction time, and then we have the permeability, which is on the nominator. So we have K, and then we have D, T, and we have also the drainage length, which is also very important here. It's different if you have a big drainage length or a long drainage length or a small drainage length. So it will depend on what this equation gives you here. So like I said, in most excavations you have undrained situation where you have stiff clay, so like very almost impermeable soils, and then you have a drained analysis when you have sandy or gravelly, and then you have the in-between that you need to evaluate yourself. So there is no clear range value where this equation gives you a definite drain or a definite undrained analysis. But it's a good approximation if you want to. In my opinion, if you're not sure, then maybe it's best if you run both types and see what is the worst case scenario. Okay, I think I've talked a lot. I see more questions, and thank you for submitting those questions. Some are very important, and I'm curious to see what you guys are doing. Again, I invite you everyone to submit your ideas for future coffee corners, either in the survey or at the ideas portal. And with that, I would like to thank you all for attending and hope to see you in the next coffee corner, which is on dynamics next month. So please stay tuned. Thank you, everyone, and have a great day and a great week. Bye.